We are up to Monday, August 15th for Math 1325, and we're going to be working on sections 7.4 and 7.5 today, and that's the end of the homework portion of the class. The final exam will appear here on Thursday and Friday, and everything for this week is due Friday, August 19th. And then since we're not doing the usual 6 or 7 sections in a week, then you get extra time to review basically. So I'll do half the review for a video on Tuesday and another half on Wednesday. There's 30 problems in there. So since there's no homework on Tuesday or Wednesday, then I can do the video for the review instead those 2 days. So in 7.4, this is the big concept of this third major part of calculus. If you do an indefinite integral 4x to the third dx, it's indefinite when you don't put any numbers here. So the antiderivative of that, you increase the exponent by 1 and then divide by that new exponent and then plus c. And the 4s would cancel out in this case. So the answer, if you were doing section 7.1 or 7.2 or 7.3, they would say the answer is x to the 4th plus c. And in some cases, then they go out of their way to give you some information that allows you to figure out what c equals as well. But generally, it's just leaving it as plus c. That's called an indefinite integral when you don't have any numbers to work with. In section 7.4, they're now going to put numbers here. We're going to have a domain to go between. So if we go between x values of 1 and 2, that's called a definite integral because it has a definite section of a graph that it correlates to. You do the antiderivative in the same way, so you're going to get x to the 4th. But you don't put a plus c. Instead, we evaluate this answer at 1 and 2. And in fact, the way it's written is you put capital F of 2 minus capital F of 1. Capital F is the antiderivative. Little f is the original function, and capital F is the antiderivative. So if I plug 2 in right there, 2 to the 4th is 16. And then plug 1 in, 1 to the 4th is 1. 16 minus 1 is 15. And what this represents in a graph, 4x to the third is a cubic graph that's vertically stretched by a factor of 4. And if you plug in 1 cubed is 1 times 4 is 4. So at the coordinate 1, 4, 1, 4, and then if you plug 2 in, 2 cubed is 8 times 4 is 32. So 232. If you connect these points on the graph to the x-axis, and this graph isn't the best because it's a little tight there, and I really should space it out more to get all the way up to 32, but using the x-axis as a boundary and these two x limits as boundaries. Really what those are is you have a vertical line x equals 1 and a vertical line x equals 2. But you stay inside the curve down to the x-axis. If you fill all that in, that's area. The area under that curve and between the x-axis, between 1 and 2, that would have an area of 15. And we can't check this like we did last time with geometrical formulas because there is no formula in geometry that would have, in essence, a rectangle with a curvy part like so that's a cubic function. So there is no geometrical formula for that. But when we did that other section where there were geometrical formulas, every problem they gave you, the picture that was drawn had some way to do it geometrically. And then we could check this calculus technique that turns out that's how that equals that. So instead of working with geometrical formulas, this is like a shortcut, and you can just do this. This is called the fundamental theorem of calculus. When you do big F of 2 minus big F of 1 to figure out how much area is under a curve from an antiderivative. Okay, so question 1. Evaluate the integral, and notice they have 1 and 6 at the two limits, which those were never there before. So in section 7.4, you always go between the curve that's given to you and the x-axis. But then next section, 7.5, then we'll go, did I say the numbers right? 7, yeah, this is 7.4, and then next one, 7.5, then you'll actually go between two different curves and the x-axis may not be involved at all. So here's an easy case where I have the integral of 7, which is a constant function, dx, that means x is the variable of interest, and it's a definite integral because it's going from 1 to 6. So first you do it like the beginning of chapter 7, and you say, what's the antiderivative of 7? The antiderivative of a constant is the linear version of that, 7x. You're increasing the exponent by 1. It went from x to the 0 to x to the first, and then dividing by the new exponent 1, so then those ones don't matter. So earlier in this chapter, you would have said the answer was 7x plus c. So now instead of putting the plus c, we're going to evaluate this from 1 to 6. And do big F of 6 minus big F of 1. Big F is the antiderivative, so you're plugging these in here. And so then I would get 7 times 6 minus 7 times 1. 42 minus 7 is 35. In fact, this one could be checked with geometry because the original function is a constant, 7. It's like the horizontal line y equals 7. That's what a constant function is. And if x equals 1, well, of course, y equals 7. Every point on the line equals 7. And if fx equals 6, f of x is f of 6 is 7 also. So these coordinates are easy to find. It's 1, 7, and 6, 7. Connect this up to the x-axis. And our area is between the two vertical lines and above the x-axis and below the curve that's involved. Apparently that area is 35, and we could check it pretty easily because this is a rectangle. The distance from 6 to 1 is 5, and this distance is definitely 7 because the horizontal line's up there at 7. The area of a rectangle is length times width, 7 times 5. It makes sense that the answer is 35. But the point is later we won't be able to check things geometrically. Here we could, but they'll get harder than that where you won't be able to do that. So here's one where the original function f of x is a linear function, 2x plus 2. We want to go from 3 to 6. From 3 to 6, 2x plus 2, that's a line. So the antiderivative of 2x is 2x to the second, and then divide by that new exponent. So these 2's are going to cancel. And then the antiderivative of 2 is just 2x. So the f of x, the original is always called f of x. F of x is 2x plus 2. But big F of x, the antiderivative, that's x squared plus 2x. And now evaluate it from 3 to 6. But in the fundamental theorem of calculus, you do big F of the higher number first, or the top number first, minus big F of 3. We say we're going from 3 to 6, but then we do F of 6 minus F of 3. So F of 6 would be 6 squared plus 2 times 6. 6 squared plus 2 times 6, and it's helpful to put that all in parentheses, because then you know when you started and stopped the F of 6, minus, now here comes another parenthesis for F of 3, 3 squared plus 2 times 3. 6 squared is 36. 2 times 6 is 12. 3 squared is 9, but this negative goes to it then. And 2 times 3 is 6, but this negative distributes in there and turns that into a negative 6. All the signs change in the second half. Remember those when we did that in limits too, how the f of x plus h minus f of x all over h and minus f of x, all those switched inside to the opposite. So now it's just 36 plus 12 minus 9 minus 6. The total area is 33. So, and again, once you get that, you're done. You can just put that answer in, 33. But on a graph, 2x plus 2 is linear, where you have a y-intercept of 2 and a slope of 2. 1, 2, 3, 4, 5, 6. Here's the whole line. But if you connect up to the x-axis at 6 and at 3, how much area is there here between the two vertical lines and between the curve and the x-axis? This is another one you can check with geometry. This is a trapezoid. So if you're going from 3 to 6, that's a distance of 3 for the height of the trapezoid. And the two bases would be f of 3 and f of 6. F of 3 is how high this is right here. That's how long this side is. F of 3 back in the original f, not the big F, the little one. 2 times 3 is 6 plus 2 is 8. So that smaller base has a height of 8. And that means this coordinate is 3, 8. And then f of 6, 2 times 6 is 12, plus 2 is 14. This is 6, 14 right here. And this base is 14. And area of a trapezoid is 1/2 base 1 plus base 2 times the height. 1/2 8 plus 14 times 3. And you should do the 8 plus 14 first, then cut that in half, and then multiply by 3. And we got the same answer, 33, as we should get the same answer. So you can even check some of these like on a test to make sure they're right. Now, once you get past basic shapes, linear stuff usually can be checked. If you have circles, they could be, but square roots, you're not going to be able to do much with that. If you have a square root of an x squared, that actually forms a semicircle, but just a square root of an x doesn't. So this one we're not going to be able to check with geometry, but now we're going to see something you saw in section 7.2. We got this 9 here that we could pull out to the front if need be. Constants can always be used while you're doing your work, or they can be pushed aside and used later after you're done with the work. So if it helps me to use that 9 anyway, I will. Otherwise, I can just push it out in front and we deal with it after we do the antiderivative. But we've got this is kind of like a chain rule where you have functions inside of functions. So the main function is a square root, but then inside the square root's a linear piece. So if I rewrite this, oops, and I forgot the numbers it goes between. It goes between 0 and 2. Okay, so I could pull this 9 out here if I want to, or I can bring it back in if I need it. And then I'm going to rewrite 4x plus 1 to the 1/2 power. So this calls for a u substitution, because 4x plus 1, the inside of the parenthesis, that can be the u, and then I would have u to the 1/2 to try to do the antiderivative of. But the derivative of that isn't just 1, so therefore that matters. Du would be 4 dx. But I don't have an extra 4. This entire 4x plus 1, that's going to be right there. I really wish there was a 4 here, though, because then the 4 dx will turn into du. And I can put a 4 there if I also put a 1/4 out here along with that 9. That doesn't help. Now, if this 9 was an 8 or even a 4, then I could get my 4 from that directly, but 4 is never going to come out of 9. So I just pushed the 9 out of the way, and then I inserted the 4 that I need. As long you can insert a constant if you need it, as long as you balance it with the reciprocal outside of the integral. And all these constants can go together and just make 9/4. And then this part's u. There's the 1/2 power. And the remaining part is how we get du. Now you actually have a choice on how you want to do the 0 to 2 part. The 0 to 2 domain, that only applies to the x variable. It doesn't apply to the u variable. So here's 2 ways you can do this, though. I got my constant. I'm going to increase the exponent by 1. 1/2 plus 1 is 3/2. Divide by that same amount. And then I can flip that and multiply by 2/3 and 2/3. So that all cancels out. 2 can go into 4 twice. 3 can go into 9 3 times. So we end up with 3/2 u to the 3/2. If you plug the x stuff back in for u at this point, then you get to still evaluate this from 0 to 2. Or you can have left it like this. If you plug in 2 right here, when x is 2, what does u equal? 2 times 4 is 8, plus 1 is 9. And then 4 times 0 is 0, plus 1 is 1. So I can either put this back as 4x plus 1 and use the original 2 and 0, or I could just leave this as u and plug in 9 and 1 instead of 2 and 0. So it's just a point of preference many times. Is it going to take long to plug 2 and 0 into here? If not, then that might be the better strategy. So then you might want to do 3/2 u to the 3/2 with from 1 to 9. And you'll get the same answer either way. If this gets real complicated and has like fractional exponents and messiness and denominators, then it's probably better just wait till the end, switch back to x and use the original ones. Or if you like one of these over the other, that's fine too. You're going to get the same answer either way, because if I'm going to be plugging the 2 in here now, that's 8 plus 1, that's 9. So whether I just plug the 9 in or whether I plug 2 in and get 9, I'm getting 9 either way. One way or the other, we have to do 9 to the 3/2. So even if I think of this as big F of 2 minus big F of 0, as soon as I plug the 2 in, the parenthesis part's going to be a 9 to the 3/2 power times 3/2. And when we plug 0 in, then you're just going to get 1 there. So that'll be 3/2 times 1 to the 3/2. Or you could even factor a 3/2 out since they both have that. 9 to the 3/2. Now 9 to the 3/2, fractional exponents, you can put that back as a radical. The 9 to the 3rd is still 9 to the 3rd, but the divided by 2 is what creates the radical. That's the square root. And you can either do 9 cubed and take the square root, or you can do the square root of 9 and then cube that answer. That's usually easier. The square root of 9 is 3, and 3 cubed is 27. And then this is the square root of 1, which is 1. 1 to the 3rd is 1. And I'd be getting the same thing if I plugged 9 and 1 in here. So again, notice I can put the 3/2 on each half and use it while I'm doing my calculations, or I can pull it out and wait till the end to do it. It turns out it's the same either way. So we're left with 3/2 times 27 minus 1. 27 minus 1 is 26. 2 can go into 26 13 times. 13 times 3 is 39. Okay, here's another one where we're going to need a u substitution. Integral from -1 to 0. Y to the 4th, and then there's a 5y to the 5th. In a parenthesis. Minus 7 squared dy. So y is the variable of interest. Usually the inside of the parentheses is a good choice to set equal to u. 5y to the 5th minus 7. The derivative of u is 5 times 5, 25. Y, decrease that by 1 to 4. The derivative of 7 is nothing, and then that's in terms of y. So this part's going to turn into u. I've got a y to the 4th dy, but I don't have the 25. So I need to insert a 25 to have everything that du has. But you can't just put one because you want it. You got to balance it with 1/25. So 1/25, the inside of the parenthesis, that's u to the 2nd power, and everything else here is du. Whoops, 25, okay. Increase the exponent by 1 to 3 and divide by 3. And then I can either create new intervals to go between. If I plug 0 and -1 in here, which isn't that hard actually, -1 to the 5th power is -1, times 5 is -5, minus 7 is -12, and plugging 0 in is really easy because it's just -7. Whoops. So we can either do this, or we can then put this stuff back in for u in the end, but once we do that, then we would go from -1 to 0, and we'd be plugging those numbers in there anyway. So 1/75 u to the 3rd power from -12 to -7. So we need to do big F of -7 minus big F of -12, and you can factor out a 1/75 and wait till the end if you want. So -7 to the 3rd minus -12 to the 3rd. So when you do a negative to a 3rd power, it will be negative. 7 times 7 times 7 is 343. Now you have this minus, and you should do the power before you subtract or even multiply. So I should do this negative 12 to the third, which will be a negative answer. It'll be negative 1728. But then it'll be minus negative 1728. So then I can turn this to plus. And then subtract 343, 1385. Times 1/75th, or just divided by 75. Does it come out evenly? No. So what do they say for the answer? They want an exact answer. So then that means 1385 over 75, and then you got to reduce it. Both of those divide definitely by 5, maybe even by 25. 75 divides by 25. Does 1385 divide by 25? No, it does not. So 1385 definitely divides by 5, though. 277. And 75 divided by 5 is 15. And this does not divide by 5 anymore. 15 divides by 3. 14 plus 2. That does not divide by 3. So 277 over 15. Okay, so what's going to happen next is we're back to another linear one, because so far what's happened hasn't caused an issue that's about to occur now. 4x minus 12. And they're giving me a domain of 2 to 6. Well, if you know 4x minus 12 has a negative 12 y-intercept, and then you go up 4 over 1, up 4 over 1, up 4 over 1 over and over again, that's what the graph would look like. But f of 2, 8 minus 12 is negative 4. F of 6, 24 minus 12 is 12. So 1, 2, 3, 4, 5, 6. So this is 612 right here. And 2, negative 4, I'll just place it here. The y-intercept was 0, negative 12. Up 4 over 1, up 4 over 1. Here, if you go up 4 over 1, you're going to land right on 3, 0. Although not that that matters, but if I just draw this from 2 to 6, because that's the domain of interest, connect those up to the x-axis, we get two triangular areas. And this is an issue that hasn't happened yet. The first 4 problems, if you were to take the time to graph them, I even graphed a couple of the first 2, but I didn't graph 3 or 4. But all 4 of those, the entire graph of where the shading would be, where the areas are, in all 4 of those, you were entirely above the x-axis the whole time. Here's the first time where part of your graph is above the x-axis and part is below. When that occurs, you have to do these definite integrals separately. I need to do a definite integral from 2 to 3, because that's where it touches the x-axis, of the original function. And then just like in geometry, if you have separate areas, you can add separate areas together. So then I can do another area for 3 through 6 of the function. Because it turns out, if you do an integral for a graph that's entirely above the x-axis, the area is positive, which is what our first 4 answers were. But if you do one that's entirely below the x-axis, the area is negative. So negative area doesn't exist in geometry, but in calculus, negative area tells you that you're below an x-axis. And if you just try to do it all the way from 2 to 6, you'll lose part of your negative aspect. So you always want to locate where is any zeros of the function, like in college algebra, so that way you can break the integral up into 2 separate parts. Because if they actually do talk about area, then you're going to take absolute values of any negative answers. So the antiderivative of 4x would be 4x squared over 2 minus just 12x. And I could reduce this down to 2x squared minus 12x. That one's going to get evaluated from 2 to 3. Now, one nice thing about these is you're doing the same antiderivative, so you don't have to redo the work. It's 2x squared minus 12x again. And then this one is from 3 to 6. So here we need to do big F of 3 minus big F of 2. And this will turn out to have a negative answer. And then this is big F of 6 minus big F of 3. There it goes, okay. So 2x squared minus 12x, if I do 2 times 3 squared minus 12 times 3, this much right here, that's big F of 3. It's negative 18. I'll write this up here, negative 18. That was big F of 3. So then if I hit second enter and just change the 3's to 2's, this will be big F of 2, negative 16. But there's always a minus right here. So this is a double negative, that'll turn into plus, negative 18 plus 16, negative 2. This little triangle has a negative 2 area. Negative 2 only because it's upside down, not that in geometry it would have a negative 2. So then I need big F of 6. Big F of 6 is 0. Minus, and we already calculated big F of 3. Big F of 3 was negative 18. Oops. That's a double negative also. 0 plus 18 is 18. So that makes sense that the bottom triangle came out negatively, the top triangle came out positively. Also, the top triangle, just as in its size, is much bigger than this tiny little one. So that kind of makes sense that it's 18 versus 2. If you care about area, if they mention area in the problem, so I'm going to check here. See, area. Area between the x-axis and f of x. If you're talking about area, then you have to do absolute values of each of these answers, although the absolute value of a positive stays positive. Absolute value negative 2 is 2. So if you just did an integral from 2 to 6, the negative 2 would add to the 18 and you would get 16 for an answer. And you wouldn't notice that part of it was negative actually. And it would not represent the total area like if you were in geometry trying to find areas, or if it's like surfaces that you're going to paint over. How much paint do I need? So by changing that negative 2 to a positive 2 just for area, then the answer is 20 instead of 16. But if they just put a problem like 1 through 4, if it just looked like this, then you would just do it and you would get 16 for the answer. Then it's okay if part of the graph is below the x-axis. But here, once it's about area, then you got to worry about above and below parts of the x-axis. So 8 minus 2x squared all the way from 0 to 7. Eight minus 2x squared, this is the original function. From 0 to 7. And it is about area, the area between the x-axis and f of x. So then we need to find any cross points on the x-axis so we can separate areas into above areas and below areas. F of 0 is definitely 8. F of 7 is not so obvious, but 7 squared is 49, times 2 is 98, 8 minus 98 is negative 90. And if x equals 0, y is 8. If y equals 0, it might not come out nice, but yeah, it does. Okay, so this is an upside down parabola that's up 8. And since 2 squared is 4, times 2 is 8, 8 minus 8 is 0. When you get to 2, that's when you're on the x-axis. And it would happen at negative 2 also, it's just we don't care about that side. But this is just an upside down parabola like so. And this is going to be hard to see it, but it crosses the x-axis twice, but it only crosses once at the part we care about. So from 0 to 2, that's when you're entirely above the x-axis. That's going to have a positive area. Then from 2 to 7, and it's off the screen a little bit, this would come down to 7, negative 90. And that's where you would draw it back up here, and then you'd have this big area below the x-axis. So this will be a large negative value below the x-axis for its area, and then we can absolute value it and turn it into a positive later. But I'm going to need to do two integrals, one from 0 to 2 of 8x squared, and then do a second one from 2 to 7. But it's the same function, so the antiderivative will be the same at least. So at least you don't have double the work, but and even the two 2's shared the same answer, so once you calculate one, you're going to have the other. So the antiderivative of 8 is 8x. The antiderivative of this is 2x, increase the exponent by 1 to 3, divide by that new exponent. Unfortunately, that'll be messy. From 0 to 2. And then you'll get the exact same antiderivative. Whoops, I wrote that wrong, but 2x cubed over 3. And this one goes from 2 to 7. So we need big F of 2 minus big F of 0. That's the fundamental theorem of calculus there. Plus, this half is just another repeated process of it. This one's big F of 7 minus big F of 2. And F of 0 is nice because that's going to be 0. If you plug zeros in here and here, they're both 0, and 0 minus 0 is 0. So for 2 cubed is 8, 16 over 3, and 16. So sometimes this doesn't come out nice. 16 minus 16 over 3. And that's also going to go at the back of this one. Okay, F of 7, big F of 7, 8 times 7, 56. 7 to the third power. Did I do third here? 2 cubed, 8. Yeah. 7 cubed is 343. Times 2 is 686. Over 3. So I'm going to check here. Do they want decimals? No, they don't want decimals. They want an integer or a simplified fraction, which is usually the case. Okay, so the first one, 16 minus 16 over 3. You could change 16 to be over 3 and have 48 over 3 minus 16 over 3. That's 32 over 3. So this has an area of 32 over 3. And notice it is positive. And if you're not good with fractions, that's where one of these could help. If you do 16 minus 16 over 3, you get a messy decimal, which they won't take. But if you do math, enter, enter, it'll turn it into 32 over 3. Okay, so that made sense that that one was positive 32 over 3. That was all the way to here. And it helped that this was 0 too. So then I need to do all this. 56 minus 686 over 3. 56 minus 686 over 3. Math, enter, enter. That's negative 518 over 3. Minus, and now this is what we got already. This part's 32 over 3. And that part's positive 32 over 3. So it's not a double negative this time. That's negative 550 over 3. So this big area right there is negative 550 over 3. So if I wasn't doing area, I would just do 32 over 3 minus 550 over 3 and it'd get some large negative value. But since you're doing area, then the absolute value of this will switch to 550 over 3. And then you can add that to 32 over 3, and you'll get a total area of 582 over 3. And does that divide by 3? Yeah, then it came out exactly to 194 at the end. But it's possible it could have stayed over 3 too. And if it was, then you wouldn't make it a decimal. But this does not divide by 3, this does not divide by 3, but when you combine them together, they do divide by 3. So 194 is the total area, ignoring the negative portion of the part that's below the x-axis. Okay, so see how this is above the x-axis, that'll be positive. This part's below. That one will be negative, and you have 64 minus x squared. So I'm going to let you do this one, number 7. I'll just set it up here. There's going to be an integral from 0 to 8. They're clearly showing where the x-intercept is 0 to 8. 0 to 8 is above the x-axis. And it's a quadratic that's upside down, 64 minus x squared. When you do this part, you're going to get a positive answer. And then I need to have a second integral that goes from 8 to 9. Yep, for a second I thought it might be 10, but no, it's 8 to 9. It's the same curve, 64 minus x squared. And it does say find the area. So if it didn't say find the area, if it was just find the integral, then I would go all the way from 0 to 9 and just in one calculation, and the negatives would make the answer smaller. But it does say area, so that's why we need to break this into 2 pieces. And this will be a negative answer once you get it. So do your antiderivatives. They're very similar to ones we've done already. F of 8, big F of 8 minus big F of 0. And since both of these will have x in their antiderivative, this F of 0 is going to be 0. It's always nice when that occurs. So this will be a positive answer right here. And it's going to have a 3 in the denominator most likely because the antiderivative of x squared is x to the third over 3. So just leave the over 3 for now over here like I did on number 6. And then add big F of 9 minus big F of 8. This is going to be a negative answer. It'll probably be over 3 also. And then when you combine then you'll want to do the absolute value of this negative to turn it into a positive. And then when you add those two positives together, you may still have over 3, or maybe you'll get lucky like my number 6 and it might not be over 3 anymore. But 7's just like 6, except they drew the picture for you. And the function's a little different. Similar deal here, go from 0 to 1 of the function, and then go from 1 to 3. And this bottom part will be negative, but then take the absolute value of it. That'll turn it into a positive. And then this will come out positive already. And then turn the negative into a positive and add the two answers together. On this one, they have 2 line segments. And then there's 2 quarter circles, they call them, 2 quarter circles. Find the value of this. Now see, this is not about area right here. So then negatives we include in the answer. And I think since they didn't tell me what f of x equals, we can't even do an antiderivative of it. This is all about finding geometrical areas. And then knowing that the ones below the x-axis will be negative, and then you'll include the negatives here because they're just doing an integral, they're not doing area. Okay, so the first little section, there's 4 sections to figure out. There's this part, which is a trapezoid, a quarter circle, and then a triangle. So the trapezoid, the height is 2. Since it's going from 0 to 2, the height is 2. One base is 1, and the other base is 3. So 1 plus 3 is 4. Half of that's 2, and then times the height is 2. That area is 4. What number is this one? 9. So that trapezoid area is 4, and it's above the x-axis, so that would stay positive 4. Then for the quarter circle, what you do is just use the area of a circle, and when you get your answer, divide by 4 since it's only 1/4 of a circle. This is a radius, a circle with a radius of 3, because notice it's 3 this way and it's 3 that way. So if you had the whole circle, it would be a circle of radius 3. Area of a circle is pi r squared. The entire circle would be 9 pi area because 3 squared is 9. But since we're only doing a quarter of the circle, then we do 9 pi over 4. And then we need to check if they want decimals or exact answers. It doesn't even say, so I'm going to assume they want the exact answer. You never put a decimal unless they ask for it. So both of those were above, then you keep them positive. Now luckily this quarter circle down here, it's the same size. It's got a radius of 3, it's just upside down. So that one's going to have negative 9 pi over 4, since it's below the x-axis. If this was talking about area, then I would change this to positive. But since it's just a integral, then you don't change it to positive. And then this may be why they didn't say if they wanted a decimal or a fraction, is because this is going to cancel that. And then finally I have a triangle that's got a height of 1, 2, 3 and a base of 1, 2, 3, 4, 5. 1/2 base times height is the area of a triangle. 1/2 3 times 5, that's 15 over 2. And it's below the x-axis, so negative. So 4 is 8 over 2 minus 15 over 2 is negative 7 over 2. And if you just do an integral, it can be negative if there's more area below than above. The 2 quarter circles have the exact same area. They cancel each other out. But the triangular area is bigger than the hexagon area, or trapezoid area, sorry, trapezoid area. So that's why the answer is negative. And then if you're not doing area, if you're not really doing area, then negatives, anything below the x-axis is negative, and that counts in the answer. If I was doing area, then I would change both of these negatives to positive, and then we'd have to add this up and you get a much larger positive answer. And you might have to approximate pi with a decimal if that were the case, but they would tell you if they wanted that or not. So that's a big difference. If you are doing these integrals and parts of the graph go below the x-axis, if you don't care about actual area, then you just do it. You just do it normally. You don't care if answers come out negative. And then if you actually had the real function, I could go all the way from 0 to 13 and just do an antiderivative all in one step. But as soon as they actually say, I want area, then any negative areas, because area can't be negative in geometry, then we have to change those to positive. Even though a definite integral its meaning actually is area, you don't do it as area unless they specifically say area. And then on this one, I guess you would have to break this in two pieces too, because the function's different in the different pieces. And notice that the break of the function is at 8. So we should do a 2 to 8 for the first function. And you should be able to do that easily. It's linear. Do an integral from 2 to 8 for 2x plus 1. And then we'll do another piece that goes from 8 to 9, was it? 8 to 9? Yeah, see, it stops at 9 for the other function. Negative 0.9x plus 8. So in a piecewise function, you definitely have to break it into two pieces at whatever the break in the domain is, like here. And this is, again, this is not about area, so you just do it entirely. Even if it drops below the x-axis, that's fine. So you would just do an integral of the first piece, and that actually is entirely above the x-axis, but that's fine. And then do the area of the other piece. And they could be pieces that connect up. You can get a piecewise function where this one goes, and then the next one picks up right there. Or they could just be different pieces like that, too. And then, in essence, you're connecting this up to the x-axis like so. And then this one could be like this, too, where you're connecting it up to the x-axis. So because the two pieces are just different functions, this curve is different than that one. 2x plus 1 is different than this linear piece, then you definitely have to do them separately. We're not doing these separately because of crossing the x-axis. That's the other time you do things separately, is when you cross the x-axis. But piecewise function, you're always going to do them backwards. I mean, not backwards, but separately. Okay, let's do one of these word problem deals. We have, see how they give you p prime of t? That's a derivative. So we're starting with a derivative function. That's what you would put here. The derivative goes in the slot to integrate. And then when I do the antiderivative of it, it'll bring me back to the regular version. They want to do this for 3 years, so it goes 0 to 3 years. So they first want to see that you're setting this up properly. Now do the definite integral of that. And this is not about area, so I'm just going to do it all together. From 0 to 3, 119 t to the 5 halves. So you got your constant, and then the base, increase the exponent by 1 to 7 halves. Divide by that same exponent, and then you can flip the second and multiply. And then we're going to evaluate this from 0 to 3. Big F of 3 minus big F of 0. Okay, does 7 go into 119? Oh, it does. That helps. 17. Okay. So we've got 34. 34, our big F function, after I did the antiderivative, the big F is 34 t to the 7/2. And then big F of 3 would be 34 3 to the 7/2 minus 34 0 to the 7/2. It's always nice to have big F of 0 in this fundamental theorem of calculus, because most of the time that whole part will be 0. Not every time. Say you have like e to the x, then e to the 0 isn't 0, it's 1. But even when it's not 0, it often comes out nicely. So 34 times 0, 0 to any power is 0, and times 34 is 0. And then you should try to do this next. No, that doesn't even come out evenly. Round to the nearest integer. Okay, so we're going to have to do a decimal here, because you can't do, I was going to do the square root of 3 first and then raise it to the 7th power, but the square root of 3 doesn't come out exactly. So square root of 3 as a decimal is there. Raise that to the 7th power and times 34. And then they said round to the nearest integer. So this is where decimals are okay, because they said to round to the nearest integer. 1590.02, that'll be 1590. Minus 0 is 1590. Okay, I'm hearing thunder outside. Hopefully I can finish this before the power goes out. So the idea here is, it says ecologists estimate the lake can accept a total level of pollution of 1,900 units before all the fish life in the lake ends. So some factory is polluting a lake and it can kill all the fish if the level reaches 1,900. But our pollution level only reached 1,590, although it's starting to get dangerous, and maybe it is killing some of the fish, but it isn't killing them all. So can the factory operate for 3 years without killing all the fish? Yes, because the value of the integral was 1590, and that's less than 1900. If it goes over 1900, then they kill all the fish. Although maybe they killed some of the fish, unfortunately. And why should they be polluting the lake to even begin with? Okay, so the rest of these are kind of similar. Try to do what you can with those. And then we're already an hour into this video. Let's make sure we cover some of section 7.5. 7.5 is area between two curves. It's really the same thing. The only difference is the second curve is not the x-axis, usually. Maybe not at all in this section. Okay, so I've got two x's as usual. That's my domain from -5 to 2. And then we're going between, well, this is an x-axis one though. But let me do one that's not first, and then I'll tell you what to do on that. Okay, this is better. Where I have two curves that are not the x-axis. Those first two basically are the same as section 7.4, because they said y equals 0 was the second curve, and that's the x-axis. So those two are done as the same as 7.4. But if I go between -2 and 2, and it does say find the area, then we got to worry about above and below areas that could be negative. So then I've got a linear piece and a quadratic piece. Y equals 10x, y equals x squared minus 11. And we're going between -2 and 2. Okay, so y equals 10x. Ten times 2 is 20, so let me go by tens here maybe. 10, 20, -10, -20. So if you plug -2 in, you get -20, that's right there. You don't have to plug -1 in, but I'm going to anyway. -1 times 10 is -10, so right there. If you plug 0 in, you get 0. And this is a linear piece, so it should line up. Plug 2 in, 10 times 2 is 20. So we have this linear piece. It's got a y-intercept of 0, a slope of 10. And now the x-axis doesn't matter, so don't worry about the x-axis. Okay, so if I plug in -2 here, it would be +4 minus 11. That would be -7, which is about right here. If I plugged in -1, it would be 1 minus 11, -10, which is the same as this right here. If I plug in 0, it's -11. And then the other side gives you the same two values as the right side did. So you got this quadratic parabola. It looks really wide just because the line has been zoomed out to intervals of 10s instead of 1s. Okay, so what happens here is connect this to this and this to that. And we got two different sections. Looks like a bow tie. So let me put it this way. They sometimes give these different names like f of x and g of x instead of calling them both y. In the left portion of the curves, the g of x, the one I call g of x, that one's above the f of x. That's similar in the previous section to being above the x-axis. And then in the other half of the graph, f of x is above g of x. So when you're doing area between two curves, you need to find points where these things intersect each other, and that's where you're going to make separate integrals. So I need to do one integral from -2 to -1, where g of x is above f of x. So then you take g of x's function and you minus f of x's function. And really this was going on before. It's just that if the x-axis is the second function, then this part is 0, and we just kind of ignored it in the last section. But technically in the last section we could have been doing that the whole time. I could have this original function, and then there's technically a -0 right there, because that's the y equals 0 horizontal line. And then I can have this one -0 too, or even 0 minus that one. So the whole key here, though, is you always want to do the above curve minus the below curve. And then if you do that, everything will come out positive here because we don't use the x-axis in any way. So then I need a second integral that goes from -1 all the way to +2. And this time the f of x would go first, 10x, minus then the other function, the g of x. And then you can clean this up before you actually do the antiderivative. Go from -2 to -1. I'll put the x squared first. Then I would put the -10x second. And then the -11. And that one's pretty easy to integrate. It's a polynomial. And then on the other one, this is where they're not going to be exactly the same. From -1 to +2, there would be a -x squared first, a +10x second, and a -11 would be a +11. In other words, all the terms switch signs. So the antiderivative of this is x to the third over 3. This one is -10x to the second over 2. -10x to the second over 2. And then that's just -11x. So in that, I need to do big F of -1 minus big F of -2. And I don't think they want decimals here. Let me check. Yeah, see, integer or fraction. So definitely no decimals. So we got to plug in -1. We're going to get -1 to the third, which is -1 over 3. -1 squared would be 1. And then -10 divided by 2 is -5. And then -1 times -11 would be +11. All of that is f of -1, big F of -1. Minus, now I'm going to do big F of -2. -2 cubed is -8 over 3. -2 squared is +4, and this is -5 here. -5 times 4 is -20. And -2 times -11 is +22. And then you got to put your negative on all three of these. So I've got a -1/3, and this is going to turn into +8/3. So that much is 7/3. And then there's a -5, a +11, -5 plus 11. This -20 will be a +20. And then this -22. So the integers add up to 4. And then you got to put that over 1 times 3 over 3. 7 over 3 plus 12 over 3 is 19 over 3. This portion is 19 over 3. The amount of area in this little triangular, it's not exactly a triangle, but triangular looking thing, that would have an area of 19 over 3. And it's positive because I did the top curve minus the bottom curve, which is always the order you should do it. Okay, so luckily out of these three then, I'm going to get the exact same 3 as here, just they're all the opposite sign. So let me do this where there's some more room. There's going to be a -x to the third over 3. There'll be a positive, and I'll make this 5 already, +5x squared. And then instead of -11x, it'll be +11x. And this goes from -1 to +2. So we need big F of 2 minus big F of -1. So you always do the larger value first. 2 first. 2 cubed is 8. So that'll just be -8 over 3. 2 squared is 4 times 5 is +20. 2 times 11 is +22. That's big F of 2. Here comes minus big F of -1. -1 cubed is -1, but then this negative turns it into +1 over 3. -1 squared is 1 times 5 is 5. -1 times 11 is -11. You need to switch all these to the opposite. I can do the integers first. 11 minus 5 plus 22 and plus 20. The integers are 8. I don't think that was right. Something's, oh, I hit minus 20. It didn't seem right. So 11 minus 5 plus 22 plus 20. Sorry, that's 48. And then there's a -8/3 and a -1/3. That's -9/3 or -3. So this area came out as an integer 45. This area is 45. And this area is 19 over 3. So our total area is 45 plus 19 over 3. Which means you need this over 1 times 3 times 3. 135 over 3 plus 19 over 3, 154 over 3, and that does not divide by 3. But it's about 51.3 total area, but we're going to leave it as an exact answer, 154 over 3. Type in an integer or an improper fraction, so you don't want to make that a mixed fraction, just leave it like that. So that's the essence of section 7.5 right there, is area between two curves. You don't care about the being above or below the x-axis. And you got to figure out if these things cross each other so that you might have to break it up into multiple integrals. Okay, cubic and a quadratic. Area between the curves. Okay, so I know what's going on there. Yeah, let's do that. Maybe this one would be good, number 5. The reason they're not giving me x values now is because, and I'm going to call this first one f of x. You might want to do that too so you keep straight which one's which. F of x is going to be x cubed minus x squared plus x plus 3. G of x is 4x squared minus 5x plus 3. So when do these things cross each other? They cross each other when they're equal to each other. So you set these equal to each other. And conveniently, the 3's could cancel out if you subtract 3 from each side. So I'm going to have an x cubed minus this 4x squared. That would make minus 5x squared. Add this 5x over, then you'll get 6x. There's a GCF of x, leaving x squared minus 5x plus 6. That factors into x minus 2 and x minus 3. They cross each other 3 times. 0, 2, and 3. And if you think about a quadratic graph like so, and a cubic graph can go like this. That's maybe not the best picture of it, but that's why they're crossing 3 times. So there's going to be an area like this, and then there's an area like that. There's going to be 2 separate areas, and apparently, as long as we know it's 0, 2, and 3, we now know where the breakups of the integral should be. But we also need to know which one's above the other one in these regions. So there's going to be a 0 to 2 integral, and then there's going to be a 2 to 3 integral. And in one of them, it'll be f of x minus g of x, and the other one, it'll be g of x minus f of x. If x equals 0, that's when they're both 3. So then a little bit past that, what if x equaled 1? If x equals 1, which one's above the other one? 1 minus 1 is 0, plus 1 plus 3, it's 4 for f of 1 here is 4. And f of 1 here is 7 minus 5 is 2. So f is the function that's above g in the first portion. Just by plugging 1 in, I could tell that. So f, it should be f of x minus g of x in your first portion. You should do this minus that in the first portion. X cubed minus x squared plus x plus 3 minus, And in essence, the minus is going to be this because I minused over there. So 4x squared minus 5x plus 3. And then in the second half, it reverses. Now the g of x function is going to be above the f of x function. So then you do g of x minus f of x. So subtracting this, we can clean this up and get it into be one polynomial, and what it should be is what I had over here, because I did subtract this and move this over. So it's x cubed, x squared minus a 4x squared is a minus 5x squared, an x minus 5x, so maybe it doesn't, wait, no, that would be plus, sorry, that is it. That's minus a negative, that's plus. So x plus 5x, that is 6x. And 3 minus 3 is 0. So yeah, it is exactly what I had. And on this one, it should just reverse. The x cubed should be negative. The negative 5 should be positive. And the 6 should be negative. So increase the exponent by 1, divide by that same amount. Increase the exponent by 1, divide by that same amount. Increase the exponent by 1, divide by that same amount. From 0 to 2. And 2 can even go into 6 3 times. So big F of 2 minus big F of 0 is this portion. Luckily, big F of 0 is 0 because plugging 0 into each x makes them all go to 0. So that's definitely minus 0 right there. So 2 to the 4th is 16. 16 divided by 4 is 4. 2 cubed is 8. 8 times 5 is 40. 40 does not divide by 3, so we need to leave it minus 40 over 3. And 2 squared is 4 times 3 is 12. I can add the 4 and 12 and get 16, but minus 40 over 3. And again, you can change 16 to 48 over 3. 48 over 3 minus 40 over 3 is 8 over 3, but if you can't do it that easily, 16 minus 40 over 3, math, enter, enter, is 8 over 3. So the amount of area in this little curvy wedge right here would be 8 over 3 is what that's saying. This portion equals 8 over 3. Plus, now we'll do this one and see what that comes out to. And everything's the same, you just have opposite signs. So there should be a negative x to the 4th over 4, a plus 5x to the 3rd over 3, and a minus, I'll write it as 3x squared. From 2 to 3. Big F of 3 minus big F of 2. And big F of 2, we just did that, that was 8 over 3. That's nice how those two, the front one here always matches the back one there. So big F of 3, 3 to the 4th. 3 to the 4th is 81, so negative 81 over 4. Three cubed is 27, but then divided by this 3 could be 9. 9 times 5 is 45. 3 squared is 9 minus, or times negative 3 is negative 27. So here's a quick way to do this. Negative 81 over 4 plus 45 minus 27 minus 8 over 3. Math, enter, enter. It's negative, shouldn't it come out negative? Negative 59 over 12. So the only thing I'm thinking is maybe it didn't do exactly what I thought it was doing in the graph. Maybe the cubic function, maybe this came like so, and then it should touch it twice though. Even if it's like that, that's not touching it twice is the only thing. That's weird that I got negative 59 over 12. Okay, let's just try this. So what if it was supposed to be 59 over 12? These should always come out positive because you're doing the above curve minus the below curve. That's always going to be positive. 59 over 12 plus 8 over 3. If the only mistake is I did this backwards, then the answer should be 91 over 12. Whoops. But if not, then there's some other mistake. Yeah, okay, I did make a mistake somewhere. See, that didn't make sense to me that was coming out negative. X to the 4, sometimes it says I can't read my own writing in this whiteboard. 5x to the third over 3. 6x squared over 2 is 3x squared. 4x squared minus 5x plus 3. 4x squared minus 5x plus 3. Okay, so x cubed is 5x squared plus 6x minus 6x, okay? Oh, I see, wait a minute. No, negative, that's it. Negative x to the third, negative x to the fourth over 4. 5x cubed over 3. Okay, so 3 to the fourth is 81 over 4. 3 cubed, 27, divided by 3 is 9, times 5 is 45. 9 times 3 is 27. Minus big F of 2. Negative 81 over 4 plus 45 minus 27. Yeah, something's wrong, but I don't want to waste time in the video trying to find. There must be a small mistake in here somewhere. How far off is it? $37 over 12. So could it be, maybe these don't cross and I should have just went all the way from 0 to 3. That might be what's wrong. Although I thought I accounted for that. If it was 8 over 3, it would be big F of 3 minus big F of 0. So negative 81, it was this right here. Math, enter, enter, negative 9 over 4. Because then it would be all the way back to 0, negative 9. Yeah, something else is wrong. I'll have to look at that. I'll let you know what I find on that one, but this is what happens sometimes where if you have I have some little small mistake where I went too big to 91, I should have stayed at 37. And then you got to go back and check all this work. There could be one little small mistake in there somewhere. And maybe it would help if I looked at the graphs too. You can also, if you graph the original functions, maybe that might help. X squared plus x plus 3 and 4x squared minus 5x plus 3. Whoops. Oh, lost it. X cubed plus minus x squared plus x plus 3 for x squared minus 5x plus 3. See, there's the cubic graph. Yeah, it's hard to tell there. Zoom in. And then it's off screen there. Okay, let's see a little bit higher. Oh no, I lost it. Okay, I thought see, it's whatever's going on over there. I can't see it. Let's get that up to maybe 10.5. So there's the cubic, there's the quadratic. It's really hard to tell what it's doing there. So let's go out to maybe 4.5 and 20.5 and go by 2s. Graph. There's the spot at 0, and then I don't think they're on top of each other, but they look like they are. And if that's the case, you would only go, no, because the answer wasn't 8/3. If it only went from 0 to 2, the answer would have been 8/3, not 37/12. But maybe it's crossing more than once, and there's the only thing. So zoom in. Let's show that. No, it's off. Okay. Well, I'll take a look at this and try to see what's going on in this problem. But this is a general idea anyway, that you try to find, if it helps to know what the graph is. So we would need to investigate this graph some more. You really need to know when these things cross each other. And I know they cross at these 3 points, or at least touch at these 3 points. So it should be like this, where it's crossing both at 2 and at 3, but it doesn't seem to separate like this, like I was assuming. Okay, so the last thing I want to show you is there's a good business problem. I think it's number 9 or 10. Yeah, this one. Find the producer's surplus. Okay, so now usually they do something called consumers and producers surplus, but this one only wants this consumer surplus. Producers, sorry, just the producers. So we get a supply curve, supply and demand from business. S of Q equals Q to the 5 halves plus 2Q to the 3 halves plus 53. And then in some problems, they give you a demand curve too. That would be D of Q. And then generally this will go, supply will go like this, and demand goes like that generally. So as supply increases, then the demand for a product decreases. That's the law of supply and demand. And then right where that intersection point is, that's called the point of equilibrium. That's where supply and demand equal each other, and that's where you should set your price to maximize everything. So they're just telling me it's at Q equals 9, but often you have to take these two and do what I did back over here. You often have to do this, where you set them equal to each other, the supply and the demand, and then you find where are they equal to each other. And sometimes it's one's on the positive side and one's on the negative side, because these curves can then meet again over here somewhere. But we don't care about negative quantities of our product. So the only one we care about here is 9. And if we plug 9 into we don't need the demand curve, but some of these problems have that. If we plug the 9 into this, the square root of 9 is 3. 3 to the 5th power is 243. The square root of 9 is 3. 3 to the third is 27. Times 2 is 54. Plus 53. The y value where this equilibrium is happening is 350. This is the supply curve. This is the demand curve, although it doesn't matter for this problem. So from 0 to 9, the horizontal line is always above the supply curve. So then we're looking for this area right here. I always remember it alphabetically C and P. C is the consumer's surplus and P is the producer's surplus. We're looking for the producer's surplus in this problem. Producer's surplus. It's going to be the integral from 0 to 9. And then you do the top curve, which is a horizontal line, minus the bottom curve. And I have to minus all three of these, so they're going to all turn negative. And then you could combine the 350 and the negative 53, positive 297. So do the antiderivative. The antiderivative of 297 is 297q. Constant turns into a linear. For the next one, you increase the exponent by 1 to 7 halves. Divide by 7 halves. And same thing here, 2q to the 5 halves divided by 5 halves. Or if I put everything in order, I can have a, flip this around and make it 2/7, negative 2/7, q to the 7 halves. Flip this around 2/5, and then times that 2 that's already there, that'll make negative 4/5. Q to the 5 halves plus 297q. That's the antiderivative, and we're doing it from 0 to 9. So big F of 9 minus big F of 0. And I only have one integral to do. I don't have to break this in pieces because the horizontal was entirely above the curve from 0 to 9. So that's why it really helps to see a graph to know what's going on. That's what I messed up that previous problem because I didn't pay attention to the graph close enough. Okay, and this is nice because f of 0, all these are going to become 0. So that's definitely minus 0. And then again, when I plug the 9 in, I just do the square root part first. The square root of 9 is 3, and then 3 to the 7th power. 3 to the 7th is 2187 times 2, negative 4374. Does that divide by 7? No, so then we got to leave it that way. Negative 4374 over 7. The square root of 9 right there is 3. 3 to the 5th was that, 3 to the 5th was that 243 number, times 4, and it definitely doesn't divide by 5, so negative 972 over 5. And then do this one times 9, 297 times 9, 2673. $26.73 minus 972 over 5 minus 4374 over 7. So there's a decimal for that. Math, enter, enter, in case they want a fraction, over 35. This one they might want a decimal because this is about money. So I'm going to put 1853.74. and the next digit's a 2, so then we don't round up. So the producers would have this much of a surplus after the law of supply and demand took effect, and the buyers and the sellers were going at it like at an auction or something. So type an integer or a decimal rounded to the hundredth. The hundredth is for dollars and cents, since this is about money. 1853.74. This is a great example of the above and the below curve. And it's a good business setting too, where it's about money. So this is always what the picture looks like. The supply curve goes up, the demand curve goes down. They have a point of equilibrium. And this problem wasn't as hard as setting them up sometimes, because sometimes they give you the demand curve too. And then you got to set them equal to each other and figure out where that point of equilibrium is. Once you get that, then you've got 0 to 9, and then you got to do the above curve minus the below curve. If you do the consumer's surplus, which this problem didn't want, consumer's surplus, then you would do the demand curve on top minus the 350 on bottom. Then it would go backwards. Then it would be whatever the demand curve was minus 350. And the demand curve would just be something totally different than the supply curve, but they didn't have that. Okay, so I'm going to try to find out where my mistake is in number 5. Something went just slightly wrong there. I need to look at it a little longer. So, but I'll email out what the mistake was, and then, or maybe you saw it while I was doing, maybe I had a brain cramp mistake somewhere in there, like a 4 times 3 and put 7 instead of 12. It could be something as simple as that. So I'll look for that and then let you know, but otherwise you should be able to handle most of the problems in 7.4 and 7.5, and just email me if you need any extra help.